Hello, welcome to the beginning of week 3, then aka chapter 3. That only works up to the first exam, really. Um, chapter 3. Well, I don't really have a good segue here. Let's just go into it. We're starting chapter 3. I don't think I sent an email out saying this. Oh, this is what I want to say. I did grade all the labs. I actually finished grading the labs Friday after they were due, and I'm pretty sure I didn't send an email out saying I finished them. I normally don't. I will almost always finish grading the labs on Friday. What I would recommend is go in and take a look where you lost points, because you don't want to make the same mistakes over and over and over again, assuming you did lose points. I'm pretty sure someone got 100. Um, so go and look. I do make mistakes, so if you see something wrong, let me know. But yeah, go check out your labs. Other than that, let's start chapter 3. And chapter 3 is called Force and Motion. It is all about forces, or at least forces and effect of forces. I'm going to be honest. I'm going to do forces basically all day today, but Wednesday I'm going to talk about a whole bunch of other things that are tied to forces. So it's all well and good to say I'm going to talk about forces, but let's start with what the hell that even means. And so, force, what it is a vector quantity capable of producing an acceleration. That's the technical definition. But basically, what a force is any time two things interact, a force is what causes the interaction. That if you go and pick something up and throw it, the reason it moves is because you applied a force. It is any time anything is being interacted with. Now, forces come in two flavors: contact force and non contact force. Contact forces are very easy. This is you push on something, you pull a spring, you pull a wagon, you kick a football. A contact force is I take this thing and I push on it. I have contact with it, and by having contact, I move it. Non-contact forces are forces where there's no physical contact. I have two magnets in my hand. If I bring this magnet close, the one jumped up towards it. The one jumped up because there was a force applied. It didn't actually connect for the force to be applied. There was no actual contact. Gravity is also a non-contact force. When you drop something, the earth doesn't reach up, grab on, and pull it down. It just falls. That's a non-contact force. Really, though, contact forces, non-contact forces, they're really the same thing. It is just something being applied to an object, making it move, or making it accelerate. I'll get into the difference there in a tiny, tiny bit. Um, in general, non-contact force, there's only really three of them. Magnets, which is what I'm playing with. Gravity, ow, that got my finger. Gravity, and electric charge, which we will cover in chapter 8. Okay. Now, for the most part, when we talk about force, we talk about net force acting on an object. See, net just means the sum of. And let's say I take this, I'm using a tape. Oh, we go with the Tetris piece. Let's say I take this Tetris piece and drop it. It falls. It falls because gravity applies a force on it. But if I go instead and place it on my hand, it's not falling. But I didn't suddenly make gravity disappear. Gravity is still affecting this. Just gravity is not pulling it downwards because my hand is holding it up. That's why we mean net force. At all times, there's normally multiple forces acting on an object, but all we care about is the sum of the forces. And by sum, I mean vector sum. If I take a rope in both hands and with my left hand, or that's probably backwards for you guys, so this is my left, pull to my left, so pull to your right, I can pull something one way or I can pull it the other. But if I take both hands and pull out evenly, neither one's budging either way. That's because the net force is zero. That it's not just the magnitude of force, but the direction. Are they left or right? And so when we're talking about force, we need to care about the direction. Anytime the sum of the forces is zero, there will be no acceleration. That something that isn't moving will stay not moving. Now, of note, The acceleration will be 0. This does not mean the velocity will be 0. Take, for example, this little car here with my accelerometer. Oh, that did weird things. Let's see if I play it again if it will play. Okay, why are you being so crappy quality? I might have to figure out what happened to this video, how it got corrupted. Oh, that was a little better. Okay. Sorry, my video is corrupted. Let me try opening it in QuickTime. I had just been messing around with these videos and I wasn't having a problem. Okay. While I'm pushing on it, there's a force. But the rest of the time when it's moving across this thing, the acceleration is barely clicking. When you say the net force is 0, that doesn't mean it isn't moving. It means there's no acceleration. That means if it was stationary, it stays stationary, or if it was moving, it keeps moving with a constant velocity. That the net force is 0 just means a constant velocity. That the velocity doesn't change. If it was 0, it stays 0. If it wasn't 0, it doesn't change 0. Now, anytime your net force isn't 0, if your net force isn't 0, if it's unbalanced, if you have forces acting on something and you sum them up and they're not 0, and when I say sum up forces, once again, we're doing vectors. I'm going to mostly define anything to the right as positive, to the left as negative, up positive, down negative, because that just matches the and I got to be careful that standard coordinate system, which hopefully isn't backwards for you. Hopefully this is pointing to the right. It's pointing to the left on my camera, but I'm pretty sure it mirrors things for you guys. So any vector. So when I say that, we got to with the vector notation. Anything pointing to the left, you got to say is a negative force. Anything pointing down, you got to say is a negative force. And I'll talk about that more in detail in a few slides. But if the net force isn't 0, if there's a net force pulling more one way than the other, what that's going to do is cause an acceleration. And then if they're not balanced, if the team on the right pulls holding the team on the left, we're going to accelerate to the right. Now, to really define forces, we're going to have to go through 3 laws. That forces were first worked out by Sir Isaac Newton, and they are based off Newton's laws. And yeah, there's the Newton's three laws. Any questions before I get into Newton's laws, though? We good so far?
Yeah.
So, Newton's first law is probably the least useful, but it's kind of interesting. Newton's law says an object will remain at rest or in uniform motion in a straight line and is acted on by an external unbalanced force. What this says is if the sum of forces is 0 or the net force is 0, the sigma just means sum of, so you could either say net force or sum of forces. Your acceleration is 0. And you can really see this here once this GIF restarts. When the bowling ball, whatever it is, first hits that trampoline, the dinosaur stays up for a little bit and starts slowly accelerating down. It doesn't instantly move down with the trampoline, but it just enters as a free fall. This is because of the fact that no force was applied to it. It just ground was moved out from under it. That things want to stay stationary. If you have no force, you have no change in velocity. That means moving things keep moving in a straight line. This goes back to centripetal acceleration. That something spins in a circle, there's acceleration. Stationary things stay stationary. Now, this is kind of hard to see on Earth because it's almost impossible to ever have 0 friction or no gravity. There's always there. This dinosaur does start to fall a few seconds after because gravity starts kicking in. But it doesn't happen instantly. It does happen instantly, but it happens slowly because of the fact that it had Newton's first law. Going back to that video I was playing, This one. That's why while I'm pushing this thing, there's a lot of acceleration because I'm applying a force. But once I'm done pushing it and once I let go, there's no acceleration because there's no force acting on it. And you can see the one light lights up a little bit. That's because there is a tiny bit of friction. But it's basically nothing because there's no force, there's no acceleration until it hits the end. And when it hits the end, there's a lot of acceleration because the end applies a force. Now, to quantize this relationship, we can say if if the sum of forces is 0, acceleration equals 0. So what happens if the sum of forces isn't 0? And how are we going to relate the two? And to do that, we need to talk about what is called inertia. Inertia is the ability to resist acceleration. Inertia is an intrinsic ability that all things have. And what it is if something is moving, it wants to keep moving. If something is stationary, it wants to stay stationary. You need a force to change. In fact, and let me see if this will work for my other videos. I have this little ball here, right? And I'm saying, if I snap the ground out from under it, the ball doesn't go flying to the side. The ball just falls straight down, despite the fact I snapped the ground out from under it. That's because the ball has inertia. It doesn't want to accelerate. And so even by moving the thing out from it, this is the idea of pulling the tablecloth out from under the dishes. They don't want to move. They want to stay stationary. That's because it has inertia. Inertia is the intrinsic ability to resist acceleration. Now, this gets really technical, and I'm going to kind of gloss over some of the technicalities here, but inertia is the ability. How we measure inertia, how we measure how much inertia something has is called mass. And really, mass and inertia are basically interchangeable. But the actual setup is inertia is what is happening, mass is a measurement of inertia. I mean, it's the only way we have to measure it. If you want to know how much inertia something has, you say what its mass is. So saying they're the same thing isn't really a stretch, but officially they are ever so slightly different. And if anything that has mass, it has inertia. It'll resist accelerations. The more mass it has, the more inertia it has. And that means the more mass something has, the harder it is to change its velocity. The harder it is to change its acceleration. This gets into, someone asked me a question about a truck, and when a heavy truck, if it's top heavy and it's starting to go, ties heavily into that idea. That the heavier something is, if it starts to go, it's going to want to keep going. This is some guy who was transporting a big ass rock that had a lot of mass. If this truck is traveling at a nice constant velocity, that rock is traveling at a nice constant velocity. If someone slams on the brakes, that's going to cause the truck to accelerate and the rock to accelerate. But if the rock has a lot of inertia, it's not going to want to change velocity. And if the truck was driving forward and you slam on the brakes, the rock will keep going forward. Anything with inertia resists acceleration. Now, this will give us the Newton's second law, where we can quantize this. Newton's second law shows the relationship between mass, acceleration, and force. And what Newton's second law says is the sum of forces acting on anything is mass times acceleration. F net, once again, is the sum of forces. M is mass, A is acceleration. And so if you apply a force, you give it acceleration. How much acceleration depends on its mass, how heavy it is. Okay. Questions? So if you want to accelerate something, you pull on it. This person, if they pull with a force F on a mass M and get acceleration A, they'll get acceleration A. If they pull twice as hard, they'll get twice the acceleration. If they make it double the mass, they'll get half the acceleration. That's the general idea. That Newton second. When I hit this little stopper here, it accelerates. How fast it accelerates, I can directly define by saying the force that stopper applied. And that wasn't the video I thought it was. Is it the video I think it is? Do you have a question? Or just okay. This one's also slightly messing up. Stupid videos. Hold on. See if this one isn't. When these two guys hit, they apply a force on each other. When they apply a force on each other, they give an acceleration on each other. And they have about the same mass, so it's balanced. But if I go and I am messing this up today. If I go and make them so they have different mass, you can see that the acceleration isn't the same for both. This code on the right has more mass, so it doesn't accelerate as much when they hit each other. Okay? So, Newton's second law. The net force equals ma. Once again, the force is what you feel. Something is pushing on you, that is the force. Force has its own special unit. If we do unit analysis, we have mass times acceleration. It's kilogram times meter per second squared. But force will get its own unit of the Newton. Newton is represented by a capital N. The American version of the Newton is the pound. That a pound is how Americans measure force. Keep in mind that F net is not just a force acting on the object, though, but the sum of the forces. Mass, once again, is the intrinsic property of something to resist motion, or its inertia. Its units is in the kilograms. The American version of mass is the slug, which is very, very, very seldom used. Now, this might seem really weird to you because I just said that pounds is a measure of force and kilograms is a unit for mass. And you probably think that they're interchangeable, like just a unit conversion, because they are just a unit conversion, right? That 1 pound is 4 point something kilograms. I don't remember the exact number. But they actually fundamentally measure different things. And here's the logic. Newtons and pounds is force. It is how hard something is being pushed on. Mass is an intrinsic ability. Mass is not, when you say how much you weigh in pounds, you are saying your weight. Your weight is not the same as your mass. And here's the idea. My mass in kilograms, sitting here, it has a set value. I could go find out what it is if I really cared. If I go to the moon, my mass in kilograms will not change. If I go to, and if I'm floating free in the middle of space, my mass in kilograms will not change. But mass in kilograms is kind of hard to measure. There's a few ways you can. If instead you go and you step on a bathroom scale, what happens when you step on a bathroom scale is gravity is applying a force downwards. The scale measures that force. Sorry, if you have a question, whoever that was, you can unmute yourself, but that was just echoing badly. Was that an actual question or just a mess up? Like seriously, you always feel free to unmute yourselves to ask questions. Okay, cool. No question, I'll keep going. So, when you step on a scale, what you get is not your mass, it is your weight, usually represented by a lowercase w. capital W something else. And weight is the force due to gravity. Your weight, my weight on Earth is not the same as my weight on the moon. And if I'm floating in space, my weight is 0. My mass on Earth is the same as my mass floating in space, but my weight is not. We interchangeably use mass and weight on Earth because the relationship is the same on this planet. You see, the weight of anything on Earth is its mass times gravity, or g being 9.81 meters per second squared. And as long as you're on this planet, always, there's a direct relationship between weight and mass. And as long as humans as a society stay just on Earth, we can use pounds and newtons interchangeably. But if we start having a moon colony, the conversion between pounds and newtons, the conversion between pounds and kilograms will be different on the moon colony than it is on Earth. Because they intrinsically measure different things. And so weight is the force due to gravity. Weight is mass times g. Weight is measured in newtons or pounds. Mass is an intrinsic property. It doesn't change where you are and is measured in kilograms. Any questions? Okay, let's do a simple problem. 11 from Stranger Things. Pose a box of Eggo waffles across the table using telekinesis. If the box of Eggos has a mass of 0.349 kilograms, what is the force required to give an acceleration of 0.215 meters per second squared? Well, net force equals ma. I'm saying, what is the net force given this mass and this acceleration? And so I say the net force would just be the mass times acceleration. And that's it. Now, this is kind of simple though, because let's think about it. If we somehow magically were pulling something with telekinesis, there'd also be some friction between the box and the table that I'm just ignoring. I'm just saying, go phew, flies through a hand. Hence the fact I decided to use the telekinesis one. Don't have to worry about that. This is it at its simplest. That F net was just the only force. Sometimes when doing these problems, there are multiple forces. If there are multiple forces on something, you got to remember that F net is the sum of forces as a vector. And we're going to define positive and negative directions. You can make it whatever the hell you want. You can pick which way is positive. You can make which way is negative. It doesn't matter. But the standard is like this. That positive x is to the right and positive y is up. That means negative x is to the left and negative y is down. What you should do is if you have multiple forces on acting on something, say any force to the right is positive, any force to the left is negative. Any force up is positive, any force down is negative. If I gave you values for the four forces on this picture of a plane, the drag, lift, thrust, weight, I would say that the drag and the weight are negative forces because they are to the left and down respectively. So they must be negative. Okay? Okay. Let's do a problem. This problem slightly exists, just me being an asshole. Because I have to do a problem talking about the force of the force, just because it makes me giggle. Though I didn't actually write this problem. It was written by a friend of mine. Darth Vader is attempting to force push Jabba the Hutt into a Sarlacc pit. Jabba has a mass of 935 kilograms. Darth Vader applies a force of 6,960 newtons by using the force. And friction applies a force F2 in the opposite direction of 3,940 newtons. What is Jabba's acceleration? So basically, we use the force to push Jabba, whew, like that. What I can do is say there's two forces here. I'm pushing him with a force F1. My force of the force is in one direction. And I said friction opposes it. I say it's in the opposite direction. That is of note. This opposite direction means it's pointing the opposite way. And what I can say is we have a mass. And we have two forces, an F1 and an F2. But the thing is, I said F2 is in the opposite direction at 3,940 newtons. What that means is F2 must be negative. That even though it wasn't written negative, it's a vector. I have to keep track of that. And because it's in the opposite direction, because this guy right here, I have to put it as negative. I have to say that it opposes the movement. And so F net is just the sum of the forces. F net is just F1 plus F2. And so F net is 6,960 newtons plus negative 3,940 newtons. And so when I sum them, I'm actually kind of subtracting them because I'm adding a negative number. That my F net is 3,020 newtons because they point in opposite ways. Still good? So I want the acceleration. F net equals ma. I can divide both sides by m, and my acceleration is then F net over m, to which I can just plug in some numbers and solve. Questions?
Yeah, where you get negative from?
Because it's to the left, because it's in the opposite direction. If it's to the left, it's going to be negative.
Oh, okay. Oh, so Fn is going. Oh, okay. F2 is going to the left, so it's negative.
Mm-hmm. I should update this problem to be Baby Yoda. Pushing something or other.
So is acceleration always, the units always meters per second squared?
Yes, the units for acceleration are always meters per second squared.
All right, thank you.
No problem. Okay. I want to real fast make sure I didn't skip a video. Nope. Okay. Okay. Let's go back to free fall from last chapter, right? I said in free fall, everything falls at a rate of 9.81 meters per second squared. That everything accelerates downwards at the same rate. And I said it didn't matter the mass, that no matter how heavy it was, everything fell at that rate. Well, in this one, I'm chapter, as in by this one, I mean this chapter, I'm saying that the force due to gravity on an object, which is the weight is the force due to gravity, is mg. And therefore the force due to gravity depends on mass. And the fact that everything falls at the same rate, but the force acting it depends on mass, seems kind of weird. But it actually works. Because if I take something and drop it, the net force acting on it when I drop it is just its weight. That when I drop on something, it's just the weight. I'm going to say it's negative because it's downwards, but that's all that's acting on it. Is the weight pulling it down. Newton's second law, F equals ma. If I say that net force is negative W, that means the negative W equals ma. But once again, the weight acting on something is mg. This is why free fall is mass independent. This is why everything falls at the same way. It's Newton's second law. It's because of the fact that acceleration is always negative g, because your weight is dependent on your mass, but so is the acceleration. So they cancel out. Okay? Okay. What's that? So, let's talk about some special forces, which we're going to do for basically the rest of today. The first special force I'm going to talk about is friction. Objects, by nature, are not perfectly smooth. That if I have, this is the back to my calculator, and I have this nice smooth piece of plastic, it's not perfectly smooth. It looks it to my eye, but really, all objects, when you go to microscopic, or not even microscopic, when you zoom in far enough, everything is rigid and spiky. And that is what causes friction. What I have here is some styrofoam blocks I made to represent this. And this is just me kind of zooming in. I'm going to cover up that picture, actually. Me zooming in on an object. If two objects are in contact, the spikiness of each surface can kind of get stuck together. Take, for example, like if you have two gears and you put one on top of the other, they'll kind of grab each other. And if you push one, it pushes the other. That's how gears work. And that's what all objects are doing on the microscopic. If the two objects aren't moving, they'll kind of settle into each other, like so. And what happens if you push an object, there we go, or pull an object, it won't want to move. Oh, there's me moving. We'll come back to me moving. Because the teeth line up. That's what friction is. Now, if something is moving, it'll kind of skip over the top like that, but those teeth will give it resistance. That resistance will make it a little hard to move versus something that is smooth. Because once again, nothing is smooth. Some things are smoother than others. That's what like Teflon is. If you coat something in Teflon, what you're doing is you are reducing, you're making it smoother than normal. But these teeth will line up. Now, friction comes in two flavors: kinetic friction and static friction. Kinetic friction is related to mu of k, the coefficient of kinetic friction, and is anytime two things are moving. When I have this, not that, when I have this sliding, kinetic friction is the friction of that movement. It is the friction of two things moving relative to each other. Note, you can have kinetic friction with zero acceleration. It just means they're moving. And it's just the idea of these teeth skipping across each other. Compare it to driving over, it's really snowing. Compare it to driving over a road with a lot of potholes. And you kind of through. That's what it is. If the objects aren't moving, that is static friction. Like so. Static friction is when the two objects aren't moving relative to each other, related to the coefficient of static friction. And static friction is kind of interesting. Kinetic friction has a set value. That the kinetic friction depends on a constant, mu of k, and not directly, but the thing's mass. There's some steps in between, but I would say it's mass for how heavy it is. Static friction is whatever it needs to be to a max value. If I go and want to push something heavy, right, and I start pushing on it, well, what's something I can make it so you can see? Let's make my camera a little bigger. Oh, hello, cat. Okay, is this okay? You can see the. Well, I'll just. Okay, my water bottle's at least the top's on the frame. If I push on this ever so lightly, it's not moving. It's not moving because the acceleration is zero. I'm applying a force, but it's not moving because friction is counteracting it. If I push, oh, that's how I should have just put on the dock cam. Although I don't know if people will let me move. And so if I push light, it doesn't move, because that means the net force is 0. That means the sum of forces is 0. That means static friction is opposing how hard I push. If I push harder and it still doesn't move, that means static friction must have increased to match. Static friction has a value of whatever it needs to be to keep something from moving, and would just be a varying thing, but has a maximum value. And the maximum value is the point at which that you suddenly, she turned it off. The maximum value is the point at which something begins to move. If you got a heavy thing and you want to push it across the floor, what's going to happen is it initially won't be moving. And if you apply more and more force, you go from applying 10 newtons to 20 newtons to 30 newtons to 40 newtons to 50 newtons. Is as you start pushing more and more, the object will initially not be moving. But the heavier you push, it'll eventually start moving. And what will happen is the force due to friction, which is my green F here, will get larger and larger and larger while it's not moving. And the force of static friction, the force of friction, will go up and up and up until you hit the maximum value of static friction. Oh, cool. She left, so I can do this here. That, my phone will work. That if I push this, you know what? I got something. Let's go back to this. It's heavier. No, it's too big. Sorry. Tape dispenser. That has a lot of friction. And so if I just push lightly, the force of static friction is how hard I'm pushing it. If I push heavier, the force of static friction is how hard I'm pushing it. And do I hit the maximum value? And once I hit the maximum value, I have kinetic friction. And the value of kinetic friction will always be a constant. Now here's an interesting thing about this. The maximum value of static friction is always bigger than the maximum value of kinetic friction. That when you want to move something, it will always be harder to make something start moving than to keep it moving. This is because if you want to make something start moving, you have to give it enough force to get it out of the teeth it's stuck in. Once it's out of those teeth, it can skip across the tops, but you need to apply enough force to get it out of that. Or fling it across the room. Does this idea make sense?
Yeah.
Now, the constants for static friction and coefficient friction. There's no values for a surface. The values always go for pairs of surfaces. If there's a value for aluminum on aluminum, there's a value for aluminum on steel, there's a value for aluminum on rubber, there's a value for aluminum on, and so on. The reason why is how much friction something feels is based off how well those teeth align. This guy that I've been doing a video of has a lot of friction because the teeth line up real well. If I switch this, and let me get the video to where I switch. If I switch this to something else that has a different shape to it, friction is going to be super low. The teeth won't really get stuck on each other because the shape of these teeth don't line up very well. And so friction will always work in pairs. What is the friction for this pair of materials? Based off how well the teeth line up. Now, if you have any machinery, you probably need oil or something to add some sort of lubrication. If you're adding lubrication, the reason that friction goes down is what you're doing is you're floating the space between the teeth. That if I have two things that are going to grind up against each other, and I can use my fingers again, and they kind of get stuck and grind. If I fill the spot with them with an oil, I'll keep them from touching. And that instead of touching, there's a bed of oil in between. I'll fill the space kind of like an Oreo cookie where the cream is lubrication. That just sounds disgusting. Anyways, bad analogy. I'm going to keep going and pretend I didn't do it. But what's going to happen is if you can keep the two things from touching and put a liquid in between, which moves freely, then you won't worry about friction. And that's why you add oil or different lubrications. You can reduce friction. Okay. Okay. 10 minutes left. Going a little slower today. So I'm going to kind of jump back for a bit. I introduced Newton's first law and Newton's second law. And then I started talking about other things. But there's actually 3 Newton's laws. And so I want to go back to Newton's laws and introduce Newton's third law. Newton's third law is commonly written as for every action is an equal and opposite reaction, which sounds fancy and people can just make all sorts of things with it. But you know, there's what the hell does that even mean? Nope, not that one. Sorry. Always the joy of me finding the right videos. You think, you know, I'd be better at this with how much we do this? Okay. Here's the idea. This cart has a spring on it. This spring on the cart applies a force to the stopper, right? The cart applies a force to the stopper. But when I do this, the cart moves. Even though the cart is what is applying the force, the cart is what goes. If I take my desk, my chair is on wheels, and push against my desk, I fly backwards. But I pushed on the desk. So I applied the force, but I felt the reaction from the force. That is Newton's third law in action. Anytime you apply a force to an object, the object applies an identical force to you. That if I have a ball, if I have 2 things that interact, and I can go back to this video I showed earlier, that if this blue call applies a force to the red call, the red call applies the exact same force to the blue call in the opposite direction. The blue call pushes on the red call with a force to the right. I'll call it F1. That means the red call applies a force to the blue call to the left with the exact same magnitude, just in the opposite direction. That's Newton's third law. That's actually how you walk. When you walk, what you do is you're pushing the earth backwards. When you push the earth backwards, the earth pushes you forwards. That is what Newton's third law is. If you got something that's going to launch a thing, you know, if a gun pushes a bullet, a gun fires a bullet to the right, the bullet's going to push the gun to the left. And the magnitude of the force is the same, just in opposite directions. Okay? I'm going to change the order of these slides for next semester. Okay. That's this question. I'm going to talk about one more special force for the day. I was going to do 2 more today, but I don't think I'll finish the second one. Let's talk about gravity. Like, we talk about gravity on Earth, everything falls at a rate of 9.81 meters per second squared on Earth. But let's talk about what gravity actually is. You see, we feel gravity from the Earth. The moon feels gravity from the Earth. The Earth feels gravity from the sun. But the thing is, gravity is a force between any 2 objects. Anything with mass will and does interact with all other things with mass. If you have 2 objects, no matter how heavy, no matter how far apart, there will be a force pulling them together. That is what gravity is. Gravity is an attractive force, pulling together everything with mass. Now, why gravity does this? That's a whole other can of worms that's still mostly theories and not really nailed down. You gotta get into modern physics. It has to do with the bending of space-time and how space-time is warped near mass. It's complicated. That's a physics 2 concept. However, the Newtonian version of gravity, which we now don't think is 100% correct on his logic, but the math works. So I'm going to teach the math still because the math does work. It says anytime you have 2 objects with mass, there will be an attractive force. The attractive force, sorry, I just heard a crash followed by an oh good in the distance. The force attracting them will go by this equation. G m1 m2 over all squared. Now all is not a radius. It is the distance between the two objects. If they're separated by 1 meter, it's 1 meter. It's the distance between the two objects. M is the mass of the two objects, m1 being one object, m2 being the other. And G, this is capital G. Lowercase g is 9.81 meters per second squared. But capital G is the universal gravity constant. It's true everywhere. Lowercase g is just Earth, but capital G is a universal thing. It has a value of 6.67 times 10 to the negative 11th newtons meter squared per kilogram squared. And says anytime you have any two objects with mass, there will be a force pulling them together. Attractive. That being said, that 9.81 number, how we got that 9.81 number was this equation. See, we can say that we are on Earth right now. As we are on Earth, we can say that Earth is one object and view us as a second object, and say the force acting on us from Earth. Well, the Earth has a set mass, and the Earth has a set radius, and G is a set value. And we can say the force of gravity on us, between us and the Earth, will be, follows this equation, where capital G will be the capital G. The M1 and M2 will be respectively the mass of the Earth and your mass. And all will be the distance from the center of you to the center of Earth. That's the thing. You just go center to center. Now, since you are much smaller than the Earth, the radius of the Earth is about the center of the Earth to the center of you. I mean, within a lot of uncertainty to not be on that. Therefore, the force of gravity acting on you would be capital G times your mass times the mass of the Earth divided by the radius of Earth squared. Here we are using radius because that's the distance from the center of the Earth to you. I do get some units to cancel out. And you get that the force acting on gravity from the Earth is 9.81 newtons per kilogram times your mass, where Newton per kilogram is the same as a meter per second squared. That's where that number comes from. Okay? So this link I just put up is kind of an interesting idea of what would happen if you had a very, very, very massive planet with a very small radius. It's kind of interesting what would happen. Read it on your own if you have time. But here's the thing. I'm saying this equation gives the force of gravity between any two objects. And you'd be like, yes, I feel gravity from the Earth. I jump, I fall. That's gravity from the Earth. But you know, I hold my water bottle in front of me. I don't feel it being pulled towards me. Gravity is sometimes called the weak force because gravity is very, very small in nature. It is only noticeable if one of the two things is super heavy, mostly because G is such a tiny number. Once again, capital G is times 10 to the negative 11. It's 0.00000000006. It's tiny. If you were to take a 1 kilogram object and a 2 kilogram object and separate them by 1 meter, I mean, a meter's decently far away, but I mean, not that far away. The force acting on a 1 kilogram object, 2 kilogram object, 1 meter away is 1.3 times 10 to the negative 10 newtons. You'll never notice the force of gravity between you and everything else because it's so small. It is negligible. It is tiny. The force of gravity is only measurable for heavy objects. Okay? Any questions? Okay, I'm going to stop there. We will pick this up Wednesday. Well, Wednesday, I'm going to introduce one more special force. I was hoping to do it today. And then we'll talk about effects of forces, things like momentum and torque, and my personal favorite, angular momentum. Have fun till then, and I'll see you
Wait, I have
then.
a question.
Oh yeah, question. What's up?
So there's nothing like on Earth that's heavy enough so that you can see that with your eyes.
No. Well, not with your bare eyes. No. And if something was heavy enough, it would start messing with Earth's gravitational pull because you'd be adding enough mass to Earth that would be messing up gravity. But no, there was nothing heavy enough on Earth other than the planet itself. I mean, the moon does apply a force of gravity on the Earth. That is what causes tides. But you know, the moon is pretty goddamn heavy compared to things we have. If you have good enough machinery, it can be measured. So with a super heavy thing, super heavy things, there is ways it can be measured between things on Earth, but they need to be, you need some real fancy machinery to do it. Okay,
Okay, thank you.
no problem. All right, other than that, I'm going to stop recording. Have a good day.